pretty much talk about electrical connectivity to three-dimensional micro nanostructures. And the thing about electric connectivity, I think the importance of that is quite obvious. No matter what type of system you do, you always need to have this electric connectivity. Right? No matter it's MEMS device, NEMS device, sensors, 3D chips, computer devices, and all that. So the importance of that is, for example, like in the IC chips and all that, we kind of pretty much know that nowadays, since there are so many kind of inputs and outputs, to the point that, flip chip that provides high density type of interconnects for you to package those chips onto a substrate, onto a package, and then in the end you assemble it into your computer devices. Or in a traditional way, people do wire bonding so that you can bond your chips to a package so that you can handle this in a much easier way and assemble it onto a circuit board. But if you look at all those interconnects here, you're talking about those bumps or those connectors in the size of about like a 50 micron or maybe to the point of maybe 10 micron. And in terms of wire bonding, like in the laboratory scale, you may be looking to like a 10 micron wires and all that. And so that provides enough kind of, for now, provides enough type of packaging capability for you to put the device into use. Now on the computer side, that limited by those interconnects, like planar type interconnects, you're also looking into nowadays into 3D chips that allow people to packaging a multiple layer of devices onto a computer chip, and in a futuristic way that people are also talking about packaging other type of devices, NEMS, food device, or NEMS devices onto your computational IC, typical IC chips. But there's a challenge into it, is that all those type of packaging, or all kind of interconnects type of technology rely on lithography. And since you rely on lithography, certainly it's good because it allows you to have a mass production capability. But in the meantime, it also restricts, in many ways, how you do those kind of interconnects. And especially, suppose you want to make high-spec ratio structures. Suppose you want to integrate it with other kind of devices, like fluid devices or MEMS devices. The limitations are always there in terms of how do you design your processing procedures to put them together. And oftentimes, when you make a design like this, it always oftentimes involves many additional steps in order to do integration. And even if you look at the 3D chips, you're talking about many processes in order to integrate the second layer to your first layer and your third layer to your second layer, in order for this whole process to be compatible. So now the issue becomes like, is there any kind of flexible ways to do some kind of interconnects, or some ways to introduce some kind of electric connectivity to your system? So we look into kind of this in an accidental way. Somehow we find it runs upon this, is that why not go back to the drawing board to think about the different ways of making metal. And when you think about making metal, you do a CVD growth, you do CVD deposition, you do epitaxial growth, you do one of the ways to the electric deposition. And when you think, so you cannot easily figure out, like when you do those type of interconnect, there's a couple of things you need to keep in mind. That one is that, is there any kind of like scale up capabilities? Second is that in terms of speed-wise, like is there a reasonable way to pursue that? And another way would be, you would think is that, how flexible is that approach? Like compared to the lithography process, can you present or provide significant amount of advantages so that in the end you will be able to pursue it? So the approach we come up with is actually quite simple. It's electroplating based, and we all know electroplating, and electroplating is based on you depart metal out through reduction out of electrolyte, and as long as you give two conductive pads, conductive electrodes, and you can perform electric deposition at least on one of the pads. So the key here is that you need to have two conductive pads and you have electrolyte. And typically when you do electroplating, you put the whole thing into a electrolyte bath. So now in order to have a controlled way to do, in that way it's like a film deposition. So in order to have a flexible way to do, for example, electric deposition, we think of what if we confine our electrolyte, for example, inside a very small pipette. and has a very small nozzle opening. And when you think of this, so now imagine you have a pen, and this pen has an ink inside, and this ink is electrolyte, so itself is a liquid state. So when you approach another conductive surface, now at the interface you would form a meniscus, but through certain kind of control. You can control the distance between them, and you can control the rate to form a meniscus. And the meniscus, in the physical sense, is very stable, actually, because nowadays, like there are certain kind of computational simulation or even experimental demonstration that you can produce a very stable meniscus down to the size of about 5 nanometer or even 2 nanometer. So meniscus, from the surface science point of view, is quite stable. But once you form this meniscus, you are forming in our case, you are forming a electrochemical cell. So when you apply voltage between them, so you have a conductor inside, and the substrate provide you a conductive path, so you can do localized electrodeposition. But if you end there, you are just producing dots. But the luckiest thing is that since you are depositing conductive material anyway, so what if you introduce some kind of motion component so that during the deposition, you actually drive this pipette in a way that you want into 3 dimensions, in the 3rd dimension. And since you always have this conductive path there, meaning that you can continue or sustain this deposition process to allow you to make wires. So now, once you have this concept, now the issue becomes, eventually, like, it can be scaled up to, like, the issue I talked about. It can be scaled up, can be competitive, and all that. Turns out it has lots of favors that in this kind of process that allow you to make this process work, or even perform better than some other processes. Turns out the existence of the meniscus, or the stability of the meniscus, provides you the exact cushion you want. Because typically when you try to deposit a small wire with small structures, suppose you through physical contact, it's very difficult to control a physical gap. But once you have the meniscus there, meniscus is stretchable. So it provides you a window of stability. And this window of stability in terms of manufacturing is very, very important. Without, everything has certain kind of instability, either through mechanical vibration, through other kind of perturbations. And since we have this meniscus, it provides enough stability, and we have analysis there that it provides a window of stability about half the size of your pipette. So if you, suppose you use a pipette of about 1 micron in opening, in terms of nozzle diameter, it actually provides you a stability about 0.5 nanometer. It means that you can stretch the meniscus even off by 0.5 micron, you would still be able to sustain the growth without breaking the growth process. And that's from the fabrication point of view, it's very, very important. So it has a self-regulated growth mechanism due to this existence of meniscus. Second is that since we are doing confined deposition, and in electrochemistry, or either kind of like mass diffusion or ion diffusion-based theory, you will find that it automatically enhances your deposition rate. For example, like in the regular type of electrodeposition, oftentimes you're practiced at a growth rate around like tens of nanometer per second. But in our process, we can get up to like micron per second. So that's almost like a 2 order or 1 order of increase in the deposition rate. And the third is that since we have this meniscus there, it provides you a channel we do all those deposition in ambient environment, certainly the controlled ambient environment. So it automatically provides you a channel for the evaporation of the meniscus, and provides so in that case, provides a high concentration zone. So you have 2 favorable things that's included in this process. First, due to evaporation, the electrolyte near that deposition interface is a high concentration. That's favorable for deposition. Second, due to evaporation, you have a mass flow involved. Mass flow helps the ion transport, and that again helps the enhancement of the deposition. So all those kind of intrinsic mechanisms favor this process to be quite unique. So what kind of problem we solved, or what kind of advantage do we have? Like, come back to the issue that we talk about in terms of providing interconnects or electrical connectivity to 3D structures. So now we have a direct write process, so it's very flexible. And it provides truly 3D fabrication because the motion path driven. You can drive the motion or drive the path of your pipette with the pretty much govern how you grow your nanowire or microwire. And the position of the confined meniscus, just like I mentioned, the meniscus can be very stable down to like a couple of nanometers, so it has much room there to push this towards nanoscale. And it operates in an ambient environment. And another thing I want to mention is that low temperature process. Electrodeposition is always a low temperature process. So it's a low temperature and ambient environment process. Simple instrumentation, purely based on nano positioning. And you have this reduced sample contamination because it's confined. Only at the place you want it to position, you have the access to the electrolyte. Electrolyte, yeah, oftentimes those ion phases are not good for lots of devices, but here we are confined. Material diversity, anything that you can do electroplating, we can make them into our system and do this type of fabrication. Unlimited aspect ratio. Aspect ratio is always a big issue in micromachining or nanolithography. You cannot, oftentimes, like through micromachining, you maybe are talking about ultimately, you're talking about be able to make aspect ratio, a structural aspect ratio of maybe like 50 to 1 or at the best 100 to 1. But in our case, it's not limited. And due to the unique type of confined electrodeposition, what we find is that all the wire will grow would be nanocrystalline and even single crystal. And the most important, we directly write solid pure metal. So we don't need to introduce a secondary process to convert our wire into a metallic wire. So it's still pure metal, and it acquires all those advantages you would have from a pure metal. So here are some results that I will just quickly run through it. So we have flexible diameter and length control. We can grow a wire from the size of 10 micron down to up to like 100 nanometer. Nowadays we can go even about 50 nanometers, and we are still pushing toward even smaller sizes. We are not limited by how high we grow. In this wire it's about 1 micron in diameter and up to a length about like 3 millimeters. So we're talking about we can directly grow a wire having a aspect ratio over 1,000 in the vertical direction, right? Vertical direction, and it's a pure metal. And we can grow this because the direct write process. We can grow this pretty much on any surface you choose. We can position. Suppose you have flat surface, that's perfect. If you just have a point source, that's fine too. We can grow this onto it. We can even grow this onto the tip, the conductive tip of FM. It's motion driven. So we can grow any kind of shape we want. So not any, but most of the shapes. So we can grow spiral-shaped structures. And if you have done micro machining, you will find it to produce a spiral-shaped structure is extremely difficult in micro machining process. Structure quality-wise, nanocrystalline. And since our growth is high kind of density type of growth, so it automatically favors the nucleation in a very fast rate, so automatically grow those nanocrystalline materials. And even single crystal. We can grow single crystal copper wires, those are copper structures. Even single crystal copper wires that with extremely smooth surface finish and a uniform diameter. And we can grow them any place you choose. So it has a patterning capabilities. And further on, we introduce some kind of concept that allow this growth to be even more flexible by shaping the nozzle. Because we have a meniscus. If you have a solid state growth, you have not much controllability. Either you do film growth or either you do a point of contact. But here, since we have meniscus, so the whole thing is about trying to introduce a new stability state for the meniscus. So imagine you have, if you cut a nozzle, it's a side opening of the nozzle. Now you can drive the meniscus in a side way. So instead of just purely vertical growth, you can grow in a different direction, vertical and all up to the point that you almost parallel to the surface. And now with this, you can think of just wire bonding. Most of you have done wire bonding, but here the wire bonding is totally different. Instead of having a fixed wire already there and try to drag this around, now we actually produce the wire in situ. Right? Produce the wire in situ from this point. You pull up, okay, you grow lateral, you push it down, and you solder it. So the step involved is pretty much similar to those wire bonding, but the difference is that now we can do sub-micron diameter wire bonding. Because the wire we produced are self-generated on-site in situ generated. It's not from an existing wire. For having a 1 micron wire, you try to drag it around. At least for now, there's no technology there that allows you to do that. But for now, in a single pad, so this pad is size about 50 micron by 50 micron. Using regular type of wire bonding on this pad, you only can make 1 bond, but we can make multiple bonds. And we can reproduce all other kind of wire bonding scenario that you have in regular type of wire bonding processes. Electrical quality, since we produce pure metal and it has extremely smooth surface finishes, we find that our electrical quality is almost comparable to the bulk value of those metal, except that, yeah, some kind of side effect will come up anyway. But yeah, it follows that same rule, and we can get a breakdown current density, yeah, down to up to like 10 to the 11th for copper and 10 to the 10th for platinum. And in terms of bonding capabilities, another issue we need to kind of look into is the bonding strength. And since this is electrical deposition process, the bond is extremely strong. So you don't need an extra way to try to increase the bond strength. And actually, the bond strength actually is much higher than this, because it turns out that when we do measurement, that this bond is electrochemically made. The other bond you have to fabricate onto it through glue or something like that. So when you try to do pull-up tests, again, the first failure point actually they are glued bond instead of your electrochemically made bond. Now, since we introduced the shaping process, we can do different shaping. Suppose you cut 2 side openings in the nozzle. Now you can imagine you can grow the wire in both directions. So you can grow this on this direction, grow this on that direction, or you introduce this kind of wavy kind of structures. Suppose you do microscale shaping, having an extension from the middle of the pipette. Now you can produce a droplet, because now it's all about the engineering, introduce the stability of the meniscus. So now you can engineering a droplet-like meniscus, a drop-like stability for the liquid. Now your direction can be omnidirectional. And indeed, when you introduce that, you can grow those coils with extremely high helical angle. And it's very stable. It's very stable. So those helical coil, yeah, having a diameter maybe about, in this one, maybe 1 or 2 microns, and we can repeatedly do that. And the ones that you can also make composite structures, we have in like vertical structures or coil structures. And further on, you can also introduce some kind of like a scanning-based meniscus, a scanning meniscus-based fabrication, and now you can make tubes down to extremely small size. And those are metal tubes without doing any kind of lithography, and you can make 3D structures on the spot of tubes. And you can shape the structure, shape those structures in this kind of direct right fashion. So in the end, now we are working towards a high-density wire array type of fabrication process, and since we have a meniscus provide our stability, so in principle there's much room for us to kind of introduce some kind of non-uniformity and all that, and be able to still sustain the continuous growth. And we are looking into some high-density microwire array that still around like 1,000 by, still around like 1 centimeter square, like a 10 micron in spacing or 1 micron in size of the wire, yeah, up to like 1,000 to 1,000 kind of array. And those might be useful for many things. And suppose you just use it as electrodes or probes. Now, since we have those array can be programmed, so now we can design those array as structural materials. We can, yeah, make it for packaging, for like high density wafer probes, for testing, for chip testing, and for micro battery and many other purposes. But one of the most exciting things that now you can potentially introduce this kind of we call it designer material, that you have the material that actually have those 3D electrical connectivity already built inside to provide you those kind of reconfigurability in terms of their electrical properties, optical properties, or just simply the mechanical properties. So those type of templates can be quite useful. And I would like end here, and I will summarize just in a single sentence saying that, yeah, there's plenty of room at the bottom, but yeah, there are lots of room over in the Z dimension. Thank you.
For the interesting talk, now we are open for questions. Yes, please.
Does the size of your nozzle affect your maximum joint speed?
I didn't include that data here. Yes. So just like I mentioned that since that we have the meniscus in between, so suppose you have a 1 micron nozzle, we have adjustment from like 1 micron down to 500 nanometers in kind of adjustability. So when you adjust, so those adjustments not by changing the size of the nozzle, by changing how the meniscus is being stretched. Right? So now in that process, yes, the growth rate will change slightly.
Next question. Yes.
So haven't you like faced any clogging problems at the nozzle tip? Doesn't the metal clog?
No, no. Unless your growth, suppose, because here's key issue here is that how you find your optimal speed for pull-up. So that speed you have to find it beforehand. But once you find that speed, now, okay, suppose the speed from say, okay, yeah, 500 nanometer per second to like 700 nanometer per second. So within this range, your wire growth will never be faster than your pull-out speed. So the only clogging issue will come up, suppose you're pulling up too slow. If you pull up too slow, the wire grows into a nozzle. Otherwise, it's purely based on electrolyte liquid, so there's no clogging issue.
Can you control whether you're growing single crystal, polycrystal, metal?
Not for every type of metal. For some type of metals, there's a process existing that allows you to grow single crystal. But we haven't tried those epitaxial type approach. Suppose you have a pure crystal, a single crystal metal surface to start with, or highly doped single crystal semiconductor to grow with, we may be able to do epitaxial. Yeah, but if you just use a regular type of polycrystalline film coating, there's only limited amount of limited selection of metal that allow you to do single crystal growth.
How are you shaping the nozzle?
What's that?
How are you shaping the nozzle?
For now, we do fiber cutting. There's not many other ways.
Any other question? Are you all ready for the reception and the poster? So please thank all the speakers this session. And,